For centuries, humans have gazed at the stars and wondered about our place in the universe. Telescopes are our eyes into the vastness of space, allowing us to see distant objects that would otherwise be invisible. But how far can these instruments actually see? The answer is complex and awe-inspiring. Our understanding of the universe is constantly evolving, with each new generation of telescopes pushing the limits of observation. From the first rudimentary refracting telescopes to today's powerful space-based observatories, we've come a long way. The quest to capture light from the most distant galaxies drives innovation in telescope technology. As we develop new technologies, we can expect even more incredible discoveries in the years to come. The universe is full of mysteries, and telescopes are our key to unlocking them. By understanding how these instruments work, we can better appreciate the incredible discoveries they make possible. The universe is a vast and wondrous place, and with each new observation, we gain a deeper understanding of its complexities and beauty. Imagine standing on a dark night looking up at a sky full of stars. Each twinkling point of light represents a distant sun, some perhaps even larger than our own. Telescopes work by collecting this faint light and focusing it into a brighter image. They act like giant light buckets, gathering far more light than our eyes ever could. Most telescopes use either lenses or mirrors to collect and focus light. Refracting telescopes use lenses to bend light, while reflecting telescopes use curved mirrors to create an image. Both types serve the same purpose, to gather as much light as possible and focus it into a clear, magnified image. But telescopes are more than just light collectors, they are also time machines. Because light travels at a finite speed, the light we see from distant objects has taken a long time to reach us. When we observe a galaxy billions of light years away, we are seeing it as it was billions of years ago. Telescopes come in all shapes and sizes, but all operate on the same fundamental principle, capturing light and revealing the secrets hidden within its faint glow. One of the most critical factors determining a telescope's power is its aperture, the diameter of its primary lens or mirror. A larger aperture allows telescopes to see fainter objects by collecting more light. This is crucial for observing distant galaxies, whose light has been stretched and weakened over billions of years. A larger aperture also increases a telescope's resolving power, its ability to distinguish fine details in distant objects. Imagine trying to read the fine print on a sign from far away. A larger pupil makes it easier. Similarly, a telescope with a larger aperture can reveal intricate structures in nebulae and resolve individual stars in distant galaxies. The quest for larger apertures has driven telescope design throughout history. From Galileo's small refracting telescope to the James Webb Space Telescope, each leap in aperture size has revolutionized our understanding of the cosmos. And this pursuit continues with even larger telescopes planned for the future. These advancements promise to unveil even more of the universe's hidden wonders. We often think of light as what our eyes can see, but visible light is just a tiny portion of the electromagnetic spectrum. The universe emits a vast range of electromagnetic radiation, from radio waves to gamma rays. Different objects in space emit radiation at different wavelengths, providing information about their temperature, composition, and motion. Telescopes are designed to detect specific portions of the electromagnetic spectrum. Optical telescopes observe visible light, ideal for studying stars, galaxies, and planetary surfaces. However, they are limited in their ability to observe objects obscured by interstellar dust. Infrared telescopes can penetrate dust clouds, revealing star-forming regions in the hearts of distant galaxies. Radio telescopes detect radio waves emitted by objects like pulsars and active galaxies. X-ray and gamma-ray telescopes study highly energetic phenomena like black holes and neutron stars. By observing the universe across the electromagnetic spectrum, astronomers gain a more complete understanding of celestial objects. Imagine trying to see a dime at the bottom of a swimming pool. The water distorts the image. Similarly, the Earth's atmosphere can blur the images of celestial objects. This blurring effect, known as atmospheric seeing, is caused by turbulence in the Earth's atmosphere. Resolution refers to a telescope's ability to distinguish between closely spaced objects or discern fine details. Higher resolution allows astronomers to see sharper images, revealing intricate structures in nebulae and resolving individual stars. Several factors influence a telescope's resolution, including its aperture and the wavelength of light being observed. larger apertures generally lead to higher resolution. Observing at shorter wavelengths, such as ultraviolet light, also improves resolution. To overcome atmospheric limitations, astronomers use adaptive optics systems. These systems use deformable mirrors to counteract atmospheric turbulence, resulting in images that rival those from space telescopes. By pushing the limits of resolution, astronomers can study the universe in greater detail. When we look up at the night sky, we are gazing into the past. The light from the stars we see has traveled vast distances, sometimes for millions or even billions of years. This means we are seeing these objects as they were when the light we see left them. The farther away an object is, the further back in time we are looking. The observable universe is a sphere centered on Earth that encompasses all the objects from which light has had time to reach us since the Big Bang. The current estimate for the radius of the observable universe is about 46.5 billion light-years. This means the most distant objects we can observe are located about 46.5 billion light-years away. The universe may extend far beyond what we can observe, perhaps even infinitely. As telescopes become more powerful, we can observe fainter and more distant objects, pushing the boundaries of the observable universe. Each new observation provides a glimpse into the universe's early history. While telescopes have allowed us to peer deeper into the universe, several factors limit how far we can see. One significant limitation is the expansion of the universe. As the universe expands, the space between galaxies stretches, causing the light from distant objects to be redshifted. The more distant an object is, the greater its redshift. Extremely distant objects are redshifted so much that their light is shifted into the infrared or even microwave wavelengths. Another challenge is the presence of interstellar dust and gas, which can absorb, scatter, and redden the light passing through them. The sensitivity of our instruments also plays a crucial role in how far we can see. Telescopes have a finite sensitivity, meaning they can only detect objects that emit or reflect enough light to be distinguished from the background noise. Extremely faint objects require long exposure times to collect enough light for detection. Finally, the finite speed of light imposes a fundamental limit on our observations. Even with the most powerful telescopes, we can only see objects whose light has had enough time to reach us since the Big Bang. Despite the challenges, astronomers and engineers are constantly pushing the boundaries of telescope technology. One highly anticipated project is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. This space telescope will survey large areas of the sky, searching for distant galaxies and studying dark energy. Another groundbreaking project is the Extremely Large Telescope, ELT, currently under construction in Chile's Atacama Desert. With its massive 39-meter primary mirror, the ELT will be the largest optical/near-infrared telescope ever built. It will be capable of directly imaging exoplanets and studying the early universe with unprecedented detail. Looking further into the future, concepts like the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, promise to revolutionize our understanding of the universe. These ambitious space telescopes would dwarf even the James Webb Space Telescope in size and capability. They will allow us to study the atmospheres of exoplanets in detail and search for signs of life beyond Earth. As we continue to innovate, we can look forward to a future filled with groundbreaking discoveries. The question of how far a telescope can see is not simply a matter of distance. It's about looking back in time, unraveling the history of the universe, and pushing the boundaries of human ingenuity. With each new generation of telescopes, we gain a clearer understanding of the cosmos. From Galileo's observations to the images captured by the Hubble and James Webb space telescopes, our view of the universe has expanded dramatically. And this journey of discovery is far from over. As we develop new technologies, we can expect even more incredible discoveries in the years to come. The universe is full of mysteries, and telescopes are our most powerful tools for exploring its depths. By capturing the faint light from distant objects, these instruments allow us to study the cosmos in ways that were once unimaginable. As we continue to push the limits of telescope technology, we can look forward to a future filled with new discoveries. We will gain a deeper appreciation for the wonders of the universe we inhabit.